Hi students, today I'm going to start Math Question Bank 15 and today we are going to discuss the very important subject of probability. Now, during the past couple of decades, probability has become extremely important, especially because data science has been booming. So that's something to keep in mind. And very often you can expect probability questions in various interviews, various tests and examinations. So we are going to briefly review this subject today through 10 questions and solutions. I am Dr. Ganguly. So let's start with some very simple questions to start the whole problem. So the question one is that a coin is flipped twice. What is the probability of two heads? Now you know that whenever a coin is flipped, it can land on the ground such that you have the heads or you have the tails facing you. So in this case, the sample space is going to be head, tail, tail, head, head, and tail, tail. So there are four possible scenarios which are possible in case you flip this coin twice. Now, the one you are interested in is the probability with the case of two heads. So therefore, we can say that the event space is heads, heads. So there is only one possibility here. So the probability can then be defined as the ratio of these two numbers. So there is 1 in the event space, that is 1 here, and there is 4 in the sample space. So in the denominator we get 4 here. So essentially the probability of getting two heads when a coin is flipped twice is 1 by 4. Now let's slightly change this problem. Once again we flip the coin twice, but now we want to know what is the probability of one head and one tail. So again the sample space remains the same, but as far as the event space is concerned, you now have two possibilities, that is head tail or tail head, and therefore the probability is going to be 2 divided by 4, which is actually half here. So you are getting the hang of the basic idea of probability, and some of the questions, of course, which are most simple involve flipping of coins. Now, the second type of question which is often asked is regarding cards. And I have seen in some cases students actually do not know the details about cards. So this is an unfair question to some students who may be coming from cultures or situations where they have never had to deal with cards. So let us just review this problem. So the question is that what is the probability of getting a picture card from a standard deck of cards? Now, the standard deck of cards actually includes 52 cards. So there are 13 spades, 13 diamonds, 13 hearts, and 13 clubs. So this is the sample space of 52. Now, as far as the picture cards are concerned, there are three picture cards for each of these situations. So if we look at spades, for example, there will be a king, a queen, and a jack of spades. If we look at diamonds, for example, there is going to be a king, queen, and a jack of diamonds, and so on for hearts and clubs. So therefore, we can see that the possibility of picture cards or the event space of picture cards is going to have 3 into 4 situations. So we can essentially calculate the probability as 3 into 4 divided by 52. So that's going to be 12 by 52 or 3 by 13. So now this is the basic concept of a standard deck of cards. Remember, there are some things known as jokers and so on. They are beyond the standard deck of cards. So always remember, in a standard deck of card, you have essentially 52 cards. So you have all the way from 1 to 10, and then you have three more cards which are the picture cards. These are the king, queen, and jack. And sometime you also have a card ace. Ace is nothing but number 1, so that is known as the ace. So let us now change this question slightly. What is the probability of getting a club card from a standard card deck? So again, we know that the possibilities here are 52. So the sample space is 52 cards, and therefore you have all these possibilities here: 13 spades, 13 diamonds, 13 hearts, and 13 clubs. And the probability of getting a club is going to be 13 divided by 52 because there are, of course, 13 club cards out there in the total of 52 cards. So the probability is going to be simply 1 by 4. Now, the third type of question which is often asked in probability involves rolling of dice. And again, there are some students who are not familiar with this concept. So if you are not, then what happens in a dice is that you have 6 possibilities here on 6 surfaces. So the possibilities are getting 1, 2, 3, 4, 5, and 6. So if you are going to roll 2 dice, then I have listed out the sample space here. You can think of this as a matrix. So we could get, for example, the first dice has 1, and the second dice could be 1, 2, 3, 4, 5, 6. Or you could have the first dice at 2, and again the second dice could have 1, 2, 3, 4, 5, 6, all the way to the point where the first dice would have 6 and the second dice could have 1, 2, 3, 4, 5, 6. So we see that the sample space has size 36 here. Now, as far as the possibilities of getting a 10 are concerned, a total of 10, there are only 3 possibilities which I can see here. That would be the case involving 4, 6, the case involving 6, 4, and the case involving 5, 5. So, in all these 3 cases, the total is going to be 10. So, 4 plus 6 is 10, 6 plus 4 is 10, and 5 plus 5 is 10. So, I can write the probability as 3 by 36 or 1 by 12. So this is the probability of getting a 10 when 2 dice are thrown. Sometimes these questions are worded like this. Actually, one could write that getting a total of 10, but people will write it like this. So you get the basic point here. The question they are trying to ask you is essentially to think about the sample space and then get the particular situations which are possible in the event space and then calculate the probability. Now let's change this question slightly. So the question becomes, what is the probability of getting a 7 when 2 dice are thrown? So again, the sample space remains exactly same. But if we look at the possibilities where the dice are summing to 7, you would have 2 plus 5, that is 7. 5 plus 2 would be 7. 6, 1, 6, 1, or rather 1, 6 and 6, 1, 3, 4 and 4, 3. So there are essentially 6 possibilities here which I can see. So immediately we can write the probability as 6 divided by 36 is 1 by 6. So this essentially introduces you to the 3 main type of problems which people ask on probability, which are related to the coin, which are related to the cards, and which are related to the dice. So let us now start looking at somewhat more complicated problems which are often used to test the students. So the question here is, what is the probability of getting a 7 or 10 when 2 dice are thrown? So we of course calculated the probability of each of these situations in the previous 2 questions. So let us now put this in a mathematical format. So A is the event of getting 7 when 2 dice are thrown, and B is the event of getting 10 when 2 dice are thrown. So you can of course imagine that these 2 situations are mutually exclusive situations, because if I am throwing 2 dice and I am totaling it to 7, that's got nothing to do with throwing 2 dice and totaling it to 10. Therefore I can say that in this particular case, what I need to find is A union B. A union B would be the situation where I get 7 or 10. So it's important to remember, whenever we are dealing with union of 2 sets, we are thinking about OR. And therefore, we can then use the standard formula for such a situation when mutually exclusive situations are taking place. So I know that PA is 1 by 6, that we saw in the previous example of getting a set of 2 dice where total is 7. PB is 1 by 12. That is the situation when the dice are totaling to 10. And therefore, PA union B equals PA plus PB, or that would be 1 by 6 plus 1 by 12. And that would be 3 divided by 12 is 1/4. So always remember that whenever we are talking of A union B, we are talking of OR. So if you have a problem where OR is involved, then you can think of A union B there. So or and A union B are the same. Now let's do a slightly more complex problem. So this is a problem where you have a group of 50 students. 35 take the GRE test, 13 take the GMAT test, and 5 take both the tests. What is the probability that a student takes the GRE or the GMAT test? So essentially you have to find PA, PB, and also you have to find PA union B. That's the question. But in this case, you can clearly see that there is a situation where a student may take both the tests, and therefore it's something where the situation is possible that there is an and here. So let's list all these things out. Let's say A is the event that a student takes the GRE test, B is the event that a student takes the GMAT test, then A intersection B is the situation where the student takes the GRE and GMAT test, and A union B is the situation that a student takes the GRE or GMAT test. So again, remember union is or, and as far as and is concerned, that is the intersection. This is something which we can recall from Venn diagrams. So now we have this formula here relating PA union B to PA intersection B and PA and PB, and in this case all these three numbers are given. So PA would simply be 35 divided by 50. So this is the probability of the students taking the GRE test. The second is 13 divided by 50, so that's the probability of the students taking the GMAT test. And then we have to subtract the situation where they are taking both the tests here, and then we get 43 by 50. So this is how you can calculate the probability in situations where there is actually a case where both these events are possible. So that's something which is happening in the A intersection B scenario. In the previous problem which we did, sometime that may be 0. So now let us formally introduce the concept of conditional probability. Of course, you are going to find details in many books, but I'm just going to lay out the formulas which we often use. So what happens in many cases is that if you have a certain sample space and two events are taking place, then the sample space is reduced due to the first event taking place. So we define something as PA slash B, and this is the probability that A occurs given that B occurred. So then we can have the formula PA slash B equals PA intersection B divided by PB, or I can write this as PA intersection B equals PB into PA slash B. So this formula is pretty ubiquitous in probability. It's actually something we can later use to derive the Bayes theorem, but let us stick with this now. Now, if A and B are such that they are independent, then PA slash B equals PA. And in that case, we can write PA intersection B is simply PB PA. That is this formula here, it degenerates to this formula here. So these are two formulas which are very important, and I'm going to illustrate these with two examples next. So let's look at this question number 9, and this question says that there is a box containing 8 red balls and 5 yellow balls. You draw a ball from the box and then put it back. You then draw a second ball from the box. What is the probability that both the balls are yellow? Now here of course this question is nice because what's happening is that you are taking out a ball and then you are putting it back. Therefore, you are not changing the sample space. So let us take the probabilities in each case. So in the case you draw the first ball, that is the event 1, the probability of a red ball would be 8 by 13. Remember, there are 8 plus 5 is 13 number of balls, and the probability of a yellow ball would be 5 by 13 because there are 5 yellow balls. Now since you returned this ball back to the box still has 13 balls, and there are 8 red balls and 5 yellow balls. So in the case of the second drawing, as far as the event 2 is concerned, again the probability of red ball is 8 by 13 and probability of the yellow ball is 5 by 13. And in this case, we clearly see that event 1 is not related to event 2. They are essentially independent. And this is because we put the ball back. So we can say that we can use the formula P A intersection B is PBPA, and therefore in this case we are simply interested in the case where both the balls are yellow. So P y intersection y would be py and that would be simply 513 by 5 by 13 and that would give me 25 by 169. So this was a problem which is relatively easy. Now in the next case we are going to do a slightly more complicated problem with the same box, the same 8 red balls and 5 yellow balls. So let's look at this particular situation that a box contains 8 red balls and 5 yellow balls, and again you draw a ball from the box and now you keep it outside the box, so you don't put it back in. So essentially what happened now is that the sample space got changed because one of the balls is out. So you had essentially 13 balls, but now you have 12 balls. Now the second case happens that you then draw one more ball from the box and then you want to know what is the probability that both the balls are yellow. So let us now apply that particular formula here. So we can see that event 1 drawing the first ball is the same as previously. So PR is 8 by 13 and PY is 5 by 13. Because there are 5 yellow balls, there are total of 13 balls. So PY is 5 by 13. But now what has happened is that one of the balls has been reduced. So as far as the event 2 is concerned, the probability of drawing the second ball is PYY is 4 by 12. So this is actually the probability after the event number 1 has taken place. So suddenly what has happened, the number of balls has reduced to 12 and the number of yellow balls has reduced to 4 provided you have taken out a yellow ball. So therefore these two are not independent anymore and therefore we have to use this formula here. PA intersection B is PB into PA slash B. So if I use this formula and I recall that I am only interested in yellow balls here, so I put A and B as both Y, then I can write this expression as 5 by 13 into 4 by 12. So the first probability here was 5 by 13, that is Py, and the second case Py slash y, that was 4 by 12. And so that's going to give me 20 divided by 156 is 5 by 39. So that's how you solve these kind of problems. So today's lecture we looked at some very simple problems in probability which can help to review this particular subject, and certainly you can ask these questions in many situations where you are interviewing for data science or anything to do with probability, maybe even machine learning. And in the next class I'm going to look at Bayes theorem, Bayes formula, which is also very important in various fields, and the conditional probability statement I discussed today, that is essentially the bedrock of how we derive Bayes theorem and how we actually use Bayes theorem. So that's something which is very important.